You should be familiar with the rules of indices from GCSE Maths, which I summarise here. We will now look at a new function which we can use to solve tough equations which involve indices. The type of equation that we are looking to solve has this form, where we know putting one number to some power will bring us to another number, and we want to know what that power is. For example, if we knew that 2 to the power of x equals 4, we would quickly deduce that x must equal 2. But if 2 to the power of x was equal to 5, it is less intuitive what x would be. Enter the logarithm function. The function looks like this, and it has an empty space for what we call the base here, and another empty space in the bracket above. If we fill the gaps with a base of a and a bracket argument of b, this function will tell us what power we would have to raise a to get to b. For example, log base 2 of 8 would be 3, since we have to raise 2 to the power of 3 to get 8. And to work out the answer to this problem, we would want to find out what log base 2 of 5 is. Generally, if x to the power of a is equal to b, then log base x of b will equal a. Since the logarithm function is designed to deal with indice problems, you won't be surprised to hear that the laws of indices lead to some laws of logarithms. I will quickly derive these rules, and as always I recommend you take your time to understand what I'm doing, but if you can't, that's fine, since all you really need for A-level are the resulting rules of logarithms. Let's consider the first rule of indices, that x to the power of a times x to the power of b is equal to x to the power of a plus b. If we call the first term in this equation alpha, the second beta, and the third gamma, the equation simply looks like alpha times beta is equal to gamma. Using our definition of the logarithm function, we see that log base x of alpha must be equal to a. Similarly, log base x of beta must be equal to b, and log base x of gamma must be equal to a plus b. Just equating these three, we see that log base x of alpha plus log base x of beta equals log base x of gamma. Since gamma equals alpha beta, we obtain the first rule of logarithms, that log base x of alpha plus log base x of beta is the same as log base x of alpha times beta. Notice that this requires the base to be the same in all the terms, which we have represented with an x here. You may not be surprised that log base x of alpha minus log base x of beta is equal to log base x of alpha divided by beta, which goes down as our second rule. If we multiply a logarithm, say log base x of alpha, by a number, let's use 3, we know that this is the same as adding 3 lots of log base x of alpha together. Using the first rule of logarithms, we realize that this is the same as log base x of alpha times alpha times alpha. In other words, log base x of alpha cubed. This demonstrates the final rule to remember, which is that log base x of alpha to the power of a is the same as a times log base x of alpha. The exponential function is centered around a very special number which we call e. E is very important in mathematics, and it seems to appear everywhere, much like pi. E, like pi, is an irrational number, which basically means that it has an infinite number of decimal places. And approximated to 3 decimal places, its value is 2.718. Like I said, this number comes up in so many places, and so it won't be a surprise that we can define it in a number of ways. One way is that it is the answer to the infinite sum of 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial and so on forever, where 3 factorial means 3 times 2 times 1. Another definition is that it's the value of 1 plus 1 over x all to the power of x in the limit that x goes to infinity. Since we are looking at indices, let's go back to the general function of a to the power of x, where a is just a constant. If we draw the graph of y is equal to a to the power of x, it will look something like this, depending on the value of a. If a is small, the graph will look more shallow, and if it's big, it will be steeper, but it will always cross the y-axis at y equals 1, and it will never quite reach the x-axis. If we set the value of the constant a to be our magical number e, we draw what turns out to be an extraordinary graph. This graph has the property that at any point on the curve, the y-coordinate at that point is the same as the gradient of the curve at that point. It is also the same as the rate of change of the gradient of the curve at that point, and the rate of change of the rate of change of the gradient at that point, and so on, forever. Let's say we had the equation e to the power of x equals some number, call it a. We know that to work out what x is, we can use the logarithm function. We just need to find the log base e of a. This type of logarithm, with e as the base, turns out to be so useful that we give it its own definition. We define log base e of a as the ln of a. The ln function is therefore a logarithm function with just one argument to worry about, since we don't need to specify the base. We know that it is e. We draw up the relationship that if e to the power of x equals a, then ln of a must equal x. Ln x and e to the power of x are therefore inverse functions to each other. If we input an argument into one of those functions and we get a result out, putting that result into the other function will bring us back to the original input. I have already spoken about the graph of y is equal to e to the power of x, and I now show the graph of y is equal to ln x, pointing out a few key features. Since they are inverse functions, the ln x graph can be remembered as the e to the x graph reflected along the line y is equal to x.